I told you last time that model reference approach implies that we're building a negative feedback system effectively. We built a system that extracts the discrepancy, the error, between the reference model and the adjustable system, and this error is utilized to come up with what we call a control effort. This control effort is supposed to be targeting the error. This control effort will eliminate the error, the discrepancy between the reference model and the adjustable system. And this would be done at the expense of some parameters or by applying special signal to the input of the adjustable system. You know, the entire system design is not a simple problem. However, in controls engineering, there are very sophisticated techniques developed to design nonlinear systems, to design nonlinear control systems. And we will utilize this mathematics, normally developed for systems with negative feedback, for nonlinear systems with negative feedback. We will utilize this approach to build or for building the model reference systems. So let me start from the point that any design problem of a model reference system could be converted into design of an equivalent nonlinear feedback system. And as soon as we will accomplish this task, we would know that some special techniques developed by control mathematicians could be utilized. I want you to consider a model reference identifier. In this identifier, we will have the reference model, and you understand that this reference model is the process that we want to be identified, the process, parameters of which we want to estimate. We have the adjustable system. This adjustable system is nothing but a simulator with adjustable parameters. And the same input U is applied to both the reference model and the adjustable system. We compute the error. We always subtract the state of the adjustable system from the state of the reference model. We have this error. We should be considering now the derivative of this error. And for the derivative of the error, we will utilize expression for the reference model and the expression for the adjustable system. And it is done perfectly. Error dot is equal to x dot minus y dot. For x dot, we have particular expression. For y dot, we have particular expression. So we subtract one expression from another. But then we can make some algebraic trick. We will add matrix AM, fundamental matrix of the reference model, multiplied by the state vector of the adjustable system. And we will add the same result, matrix AM of the reference model multiplied by the state vector of the adjustable system. There is no any special meaning for this procedure, except it will help in our derivation. After this is done, we can define the derivative of the error as matrix AM, fundamental matrix of the reference model, times the error, plus this expression. And you understand that the adaptation procedure is the procedure that defines matrix A of the adjustable system as a function of error and time, and probably it should have some initial value plus some function of error and time, and we will call this function f. We could use any notation for this function. Similarly, the adaptation mechanism for matrix B of the adjustable system is defined as some initial conditions plus some function g of error and time. And then we can consider expression for the derivative of the error. Error dot is equal to fundamental matrix of the reference model times error minus this expression. Minus this expression, and in this expression, matrix A of the adjustable system is defined according to this expression, and matrix B of the adjustable system is defined by this expression. I want you to take a close look at this expression, what it reminds you of. I would say that it could be perceived as conventional state variable description of a dynamic system, except the reference or input signal is defined by this expression. We always have this E dot is equal to AM times E plus matrix B times the external signal. This looks like matrix B times external signal in our system. And I would say that this expression could be rewritten further. This is another expression, but now you can take a look at this expression, at this one, from the following position. It looks like we're dealing with a linear dynamic system, and the fundamental matrix of this system is matrix AM, and we have nonlinear signal that drives this linear system. And the signal is defined obviously by this nonlinear expression. So it looks like what we have here is a nonlinear time varying negative feedback closed loop system. What we have is effectively this is represented by this configuration. We have a linear time invariant forward path. We have controlled variable is E, the error. We have error is picked up, and we compute a nonlinear function of this error. Error is multiplied by state vector y, error is multiplied by control effort u. This is a nonlinear expression. And this nonlinear expression results in a feedback signal. And this feedback signal is applied to the summing junction. You may ask me, where is the reference? If it is a control system, where is the reference? Don't forget, this control system is supposed to control the value of error, and the reference supposed to be the desired value of this error. This is what reference is for, and obviously reference is 0, so we don't have this error, desired value of the error shown in our expression. We have expression for the linear forward path, and we have expression for the nonlinear feedback. Again, why it is nonlinear? It is nonlinear because function of error is multiplied by the state vector. Function of error is multiplied by the input signal u. We never saw it before. We have one signal is multiplied by another signal, and this is the control law. Now, what do we want to happen? We want this system to be globally asymptotically stable, which means that for any initial conditions, for any initial value of this error, as time approaches infinity, this error supposed to approach zero, global asymptotic stability. Now, how to achieve this global asymptotic stability for our nonlinear system? Fortunately, control engineers, control mathematicians came up with a very special approach for addressing this problem. And we will utilize this approach. And as a matter of fact, there are two approaches that we can utilize. How it could be utilized? What this approach will require us to do? We have to impose special conditions on this linear time invariant part. And we will have to impose special conditions on this nonlinear time varying part. Conditions are mathematical conditions. Now, we will do something now that we have to do because we are concerned about making this linear part flexible enough so that we would be able to impose these conditions. And we will do something about this nonlinear part. We have to make sure that it is flexible enough so that these special conditions would be or could be implemented. With the linear part, it's easy to do. We have to introduce special filter G. We have to insert right here special filter G that would convert error into an intermediate variable V. This is easy. And if we will introduce this filter G, linear part will continue to be linear. The nonlinear part for this flexibility should be defined by this integral plus proportional plus initial condition expression. And for matrix B, it should be the integral of some vector matrix function psi plus matrix function psi2 plus initial conditions. Don't look for any physical meaning of this definition. No, this is something that enables us to come up with flexible expressions because we want to bend this nonlinear part to special mathematical requirements. And this is what we will get as a result. Our system supposed to be represented by this configuration. Linear time invariant part now has specially defined matrix D. And in the nonlinear part, we will have to define matrix function psi2, psi1, phi2, and phi1. And as I said, to achieve global asymptotic stability, G has to satisfy some requirements, and these functions supposed to satisfy some additional requirements. We will get into this. It is not that simple to do, and we will do it. However, there are problems that do not require us to be so mathematically rigorous. We will try to come up with an approach that would not involve building this linear time invariant part and nonlinear time varying part that satisfies special conditions. There are basically three ways of doing it. The first approach is known as local parametric optimization. It is very straightforward. It does not involve working on the negative feedback nonlinear system. But then there is a much more powerful approach, the Lyapunov functions-based approach. And then there is approach known as hyperstability and positivity. What's good about all three approaches, and what is my responsibility with respect to all three approaches, I will show you problems that could be practically solved by any successful student in this class. We will start from local parametric optimization approach. This local parametric optimization starts from the assumptions. You see, it's not global asymptotic stability at all. Actually, later you will realize that local parametric optimization is a technique that sometimes works, but this technique does not imply the use of any stability conditions. All right, so our first assumption is that initial errors in the system are small, quite small, which means that initial discrepancy between the state vector of reference model and adjustable system is quite small. In the case of parameter estimation, initial discrepancy between matrix A of the reference model and matrix A of the adjustable system are small, and the same is true about matrix B of the reference model and matrix B of the adjustable system. The second requirement implies that the speed of adaptation is low, which means that if this system is a dynamic system, if we're dealing here with a dynamic system, this dynamic system is supposed to have its settling time, and with respect to the settling time, the adaptation, the convergence of our adaptation procedure is much, much slower than the settling time. What is the essence of the local parametric optimization? First of all, we have to define a performance index, a criterion that represents the effectively the distance, the goodness of the adjustable system with respect to the reference model. And this criterion should be dependent on the adjustable parameters. And then we will come up with a way to minimize this performance index with respect to adjustable parameters using a specific optimization approach. And the optimization approach that we will use here is the gradient minimization. Some of you may be familiar with gradient minimization. Some of you will hear about it first time, but the story is this. Let's assume that we want to minimize some quadratic function, function q. It depends on vector x, and in my example, x has three components, x1, x2, and x3. Which means that our goal is to find such x star that consists of x1 star, x2 star, x3 star, such that for any value of the state vector x at the point x star, value of the criterion reaches its minimum, is the smallest. What's next? We will have to start from some initial condition. So we will start from some point x0 such that the distance between point x0 and the point of minimum is small. Without this condition, we may have a lot of computational difficulties. And then imagine that at location x0, we're taking derivatives of the criterion with respect to x1, x2, and x3. And each of these derivatives is a scalar, but they could be organized into a vector. And this vector is called gradient. And don't forget that this gradient is defined at one particular location in the x space, at the location x0. You know what's special about this gradient? Gradient is a vector, and this vector is always pointed in the direction of the increase of function q. Increase. Now, what if we will move not in the direction of the increase of function q? What if we would move in the opposite direction? Then we're supposed to reach the point of minimum. So gradient numerically is a combination of derivatives taken at a particular location in the space x. But we should consider it, we can perceive it as a navigational instrument that enables us to make steps in the appropriate direction. And our direction is the minimum of the criterion, Q. How do we move in the direction of minimum? If we would increment state vector x, the increment should be equal to minus, then we would need a positive constant, and then we would need a gradient. We need a gradient. Because if we would not have this minus, then delta x would be an increment in the direction, or increment that would result in the increase of the criterion. With minus, this increment is supposed to lead to the decrease of the criterion value. K is a scaling factor that determines the size of the increment. Now, practically what we will do, we will have an increment for every component of the state vector x. It would be delta x, defined as minus constant times derivative of criterion with respect to this x, delta xj, or delta x1 would have derivative of the criterion with respect to x1, delta x2 will have derivative of the criterion with respect to x2, and so on. It also makes sense to consider the rate of our motion, or the velocity of this motion, because we are supposed to repeat the steps again and again and again, moving more and more close to the minimum point. If I would take derivative of delta x, I will get this velocity v, and this velocity will have three components in my case, and each component will be partial derivative, will be time derivative, or delta x of delta x1, delta x2, and delta x3. So the combination of this time derivative with respect to, or taken off components delta x, delta x1, delta x2, delta x3, will give me the vector of velocities, or rate of change of parameters. But you know what? This is the derivative taken of delta xj, but the order of differentiation, as you're supposed to know from your calculus, could be always changed. So, So, when we take this differentiation, we have one differentiation with respect to time, we have another differentiation with respect to x to adjustable parameter, and order of these differentiations could be always changed. If derivatives are utilized to define increments or describe the motion of the system towards the minimum point, then of course you can say that the minimum point of minimum, x1, x2, x3 with star could be defined as initial conditions, plus the integral of the appropriate velocities with respect to time, and we integrate from 0 to infinity, which means that if we would perform theoretically infinite number of steps, we would reach the minimum point, or every coordinate, every component of the minimum point will be reached. What is the importance of the good initial point? The importance is this. If we will not start from good initial point, gradient as the minimization procedure does not guarantee that we will reach the necessary point. Okay? So there are many problems where it is difficult to assure that you will get exactly to the unique minimum point. Number of minimum points could be more than one. So this is keep in mind. There are global minimum points, there are local minimum points, because function q of x could be quite complex. The best what we can do at this point is to give you example of local parametric optimization. We will consider a system reference model reference-based system that performs parameter estimation. So, for the reference model, I have this differential equation. I'm assuming that S, Laplace variable, is symbol of differentiation. This is the output of the reference model. This is the denominator of the appropriate transfer function. This is the numerator, polynomial numerator of the appropriate transfer function. And rho is the input. We have the parallel configuration. Therefore, the differential equation for the adjustable system is very similar by its structure. However, alpha, and alpha, beta 2, beta 1, and beta 0 are adjustable. It's a parallel configuration. Error is defined as the output of the reference model minus the output of the adjustable system. The criterion is defined as an integral of the error squared. The meaning of this criterion is very clear. If this criterion is minimized and if it reaches 0, we basically can claim that the reference model and the adjustable system have identical responses to the same input. What is special about 1 over 2? We will be doing some differentiation, so we do not want to place multiplier 2 in front of the expression as we do the differentiation. This is the system configuration. The adaptation mechanism supposed to be responsible for the definition of beta 2, beta 1, beta 0, alpha 3, alpha 2, and alpha 1, based on the expression of the error, and perhaps some additional factors should be included. Listen, you have to realize that if alpha 3, alpha 2, alpha 1, beta 2, beta 1, beta 0 are properly defined, then the criterion will reach smaller value. If they are improperly defined, the criterion value will increase. Effectively, the criterion Q is a function, quadratic function, of the adjustable parameters. So our goal is to come up with such values of these adjustable parameters that would minimize the function Q or criterion Q. The requirement of good initial conditions is right here. We are assuming that for every alpha in the beginning of our process, the distance from the corresponding A parameter of the reference model is small. The same is true for parameters beta. Now we will take use of the gradient procedure. This is the increment of parameter alpha. This is the increment of one of the parameters beta. It is equal, unsurprisingly, to minus, because we're moving in the point of minimum, to the point of minimum. It has the constant k, and then you have the derivative of the criterion, which actually is a component of the gradient. The same is true for increment of beta. It has minus, because we're supposed to move towards the minimum point, not towards maximum, but to the minimum point. And then you have parameter k that determines the size of the step. It's a kind of scaling factor. And then we have derivative of the criterion with respect to parameter beta. Then we will get into the definition of the rate of parameter change. To determine the rate of parameter change, I will take derivatives, time derivatives, of delta alpha and delta beta. And this is the honestly written derivatives, time derivatives of the expressions of the components of the gradient, actually. The next, what we will do, we will honestly compute time derivatives that were mentioned here. This is d over dt of the component of the gradient. You know that the order of differentiation could be changed. I told you about this. So first we will do d over d alpha. And then we will be taking the time derivative of this integral of the criterion. And don't forget, criterion is the error squared. So if we would do this computation properly, and I'm assuming that you still remember how to take derivatives of a quadratic function, this is the result that we will have. You may ask me, what happened to the minus that was there? You know, we're taking derivative of the error. But error is defined as a difference between theta model and theta system. But theta model, output of the model, does not depend on the parameter alpha or parameter beta. So we're taking derivative only of the theta. But theta comes with minus. So first, we have to realize when we take these derivatives, minus will reappear. But then you have to realize that since we're moving in the direction opposite to the direction of gradient, these minuses will disappear. And what we have finally is the rate of change of parameters alpha 1, alpha 2, alpha 3, which is defined as plus positive constant k times the error times the derivative of the output of the adjustable system with respect to parameters alpha 1, alpha 2, alpha 3. And the same is true for the rate of change of parameters beta dot. It is equal to a constant times the error times the derivative of the output of the adjustable system with respect to beta 1, beta 2, and beta 3. You know, formally, we can use these expressions as the components of the adaptation mechanism. Actually, this is adaptation mechanism, because if we would integrate these expressions, we will be able to obtain the alpha 1 star, alpha 2 star, alpha 3 star, and so on. We will be able to get to the minimum point, at least theoretically. However, these functions are derivatives of the output of the adjustable system with respect to parameters of the adjustable system. They are known as the sensitivity functions. And there are many cases when taking these sensitivity functions is not practical. So we may consider working further on these expressions. Let's recall the differential equation of the adjustable system. You know, don't be confused. I called once this parameters S. It used to be S. This is also S. This is S, S, and S. These parameters S were Laplace variables. But Laplace variables often used as the symbol of differentiation. So you see, it's not a big deal to rewrite this expression first in this form. And second, let's call these parameters P what they actually are. They are symbols of differentiation. Multiplication by P cubed implies taking third derivative. The multiplication of P squared is second derivative, and so on. And I could easily use variable S instead of P, but it doesn't make any difference. So now what we can do, we have this expression for us. And what we can do now is we can define derivative of theta s to parameter alpha 1. Consider taking derivative of theta s with respect to parameter alpha 1. What is it? This derivative, I know you understand how to take derivatives, so look at this expression. I'm taking derivative of theta s with respect to parameter alpha 1. What is it? It is derivative of theta s. Derivative of theta s, and it comes with minus. I'm taking derivative of theta s with respect to alpha 2. Look at this expression. It is theta s with two dots, second derivative. And similarly, and with minus sign, and similarly, taking derivative of theta s with respect to alpha 3 will give you third derivative of theta s with minus. So this is something that we will do, and we will utilize this in the adaptation mechanism. Look, the same story is about derivatives of theta s with respect to beta 0, beta 1, and beta 2. These derivatives are equal to input signal raw, to derivative of input signal raw, and to second derivative of input signal raw. So now we can redefine the adaptation mechanism using not the sensitivity functions, but using the derivatives, time derivatives of the output of the adjustable system and time derivatives of the input signal raw. You know, this approach became known as the MIT rule. I can imagine that somebody at MIT invented this approach. How it works? So-so. You know, I even stopped giving students assignment to implement the system in simulation. You have to be really very close to unknown parameters of the adjustable system, unknown parameters to the reference model. The initial discrepancy between parameters of the adjustable system and reference model should be really very small, and then this approach will work. I will consider with you a different modification of this approach. I am not a big fan of MIT rule. Sorry. Well, if you would follow the MIT rule, obviously that the adaptation mechanism is as follows, because in order to get adjustable parameter alpha 1 should be defined at its initial value plus this integral of the rate of change. Parameter alpha 2 as a function of time should be defined as initial conditions minus this integral, and so on. And so on. Now, the approach obviously has nothing to do with system stability. If you're lucky, your system will perform properly. If you are not so lucky, your system can easily diverge and you will get absolutely no result. This approach is good on paper, but it requires too much of good luck. But when it works beautifully. Why we cannot assure that it works each time we use it? Because in this approach, we do not have incorporated stability conditions. I want to consider with you a simulation study of the model reference parameter identification system using local parametric optimization. I am not using the MIT rule. I am doing just gradient minimization. And I want you to see what is done. First of all, you understand that the input signal is X, and the input signal is applied at the same time at the reference model and at the adjustable system. The output of the reference model I call Y. The output of the adjustable system I call YT, and this big T stands for theta, YT. And this is minus. So at this location I define the error as the output of the reference model minus the output of the adjustable system. And here I create error squared. And this is this is the criterion Q value. What is about the reference model? For the reference model, I use very straightforward transfer function. It's a stable system, a third order system. For the adjustable system, the capabilities of my software with SIM are limited, So I have to create a simulator for this adjustable system where parameters could be tuned, could be adjusted. Because in this system, parameters could not be adjusted. If it's 8, it's 8, cannot be changed. However, here, in this configuration, every single parameter of exactly the same transfer function is defined by variables. These variables are b theta 2, b theta 1, b theta 0, a theta 2, a theta 1, a theta 0. How I created the simulator? If you remember signal flow graph from your first controls class, this is what I use to build the simulator for the adjustable system on. What you can see here is the definition of the reference model and the definition of the adjustable system, and this is the definition of the error. And now you can see the adjustable parameter beta tilde, beta 2, beta 1, beta 0, adjustable parameters alpha, alpha 2 is a function of error and time, alpha 1 function of error and time, and alpha 0 is a function of error and time. And this is the criterion defined here. Criterion is error squared, but error squared is the difference between the output of the reference model and output of the adjustable system squared. And this is the same expression, except the output of the adjustable system I defined as a product of the transfer function with adjustable parameters and the input signal x. I want you to see what is being done. I am taking the partial derivative of the criterion with respect to parameter beta 2. First of all, I have minus. I need this minus because I plan to move in the direction opposite to the gradient. This 2 comes into play because I'm taking derivative of a squared function. The squared function that I have in these square brackets. So, minus 2 times the square bracket is the derivative of the quadratic function. Now I'm taking the derivative of the inside of what I have in the square brackets. So what do I have? I have the partial derivative of this expression, with respect to beta 2. Minus disappears, supposed to disappear, because this expression has its own minus. We will see what happens with the minus. I'm not sure what happened with the minus. Look, I'm assuming, I guess, that this minus comes from the necessity to take derivative of this expression. And this expression has its own minus. This is why I have minus. So one way or another, I have minus, I have 2, I have this expression in square brackets, but by the way, it is nothing but the error. Look, This is the output of the reference model. And this is the output of the adjustable system. This is the error. Now, if I would take derivative with respect to B2 parameter, what will happen? This is what will happen. S squared will stay, denominator will stay. So look, this is the result of the representing the derivative of the criterion with respect to parameter B2. There is no mistake in this result, actually. There is no mistake in this result. I have -2, I have error, I have this symbol S squared. This symbol S squared is symbol of derivative that will be applied to this input X. And I have this denominator. The next, what I am doing here, it's a mathematical simplification. I will assume that this denominator is not much different from the denominator of the adjustable system, because local parametric optimization implies that the initial difference between the adjustable system and the reference model is small. So I am rewriting this result. Now I have -2, I have error, I have S squared, symbol of the second derivative, that is applied to X, input X, and I have the denominator of the reference model. Very similar result I am getting right here for the derivative with respect to B1, parameter B1 tilde. And similar result I have when I take derivative with respect to parameter B0 tilde. I want to reiterate, having S squared in this expression and having this multiplication by X of S implies that this expression will contain second derivative of X of S. Having S in this expression and having this multiplication by X of S implies that this expression will contain first derivative of X of S. And not having S in this expression and having this multiplier X of S implies that derivative is not taken of the signal X. Signal X of S will be used as it is. I have a little bit more complex task. When I will be taking derivative of criterion Q with respect to parameters alpha, because parameters alpha tilde, parameters A, because parameters A tilde are in the denominator. Look, I have this minus because of the expression in the square brackets has minus in front of the part dependent on parameter A2 tilde. Then I take derivative of expression in square bracket with respect to parameter A2 tilde. You remember probably how to take derivative of a ratio with numerator and denominator. So I have minus, I have expression of the denominator squared, and the numerator works as a constant coefficient here. So look, I'm going through this process very carefully, and eventually I'm getting, minus would disappear, and I'm having 2 because of the quadratic expression for the criterion, multiplied by the error and multiplied by the S squared, multiplied by the output of the adjustable system, But s squared times output of the adjustable system is actually second derivative of the adjustable system. And I have this denominator, the characteristic polynomial from the adjustable system. But since initial conditions of the adjustable system and the reference model are closed, I'm just replacing this expression by the denominator of the reference model. So final result is plus 2 times error times second derivative of output of the adjustable system divided by the denominator of the reference model. Similar expression I'm getting for the derivative of the criterion with respect to parameter a1 tilde and parameter a2 tilde. And now I want you to take a close look at the implementation of these partial derivatives in the simulator. Look, I have input x. This input x is multiplied by this transfer function. Denominator of the transfer function is the denominator of the reference model. In the numerator I have s squared, which implies that second derivative of x will be taken. This is multiplied by the error, and I'm taking it with minus. You may ask me, where is 2? We will discard 2. It will be absorbed later by some constant gain, adaptation gain. This is expression for partial derivative of criterion with respect to parameter b1. I have x input multiplied by s, which means I will have first derivative of x. I have this denominator of the reference model. It is multiplied by error, and I have minus. So this is the derivative. This is the third derivative, and here I have 3 derivatives of the criterion with respect to the parameter a2, parameter a1, and parameter a0 of the adjustable system. What's interesting is this. Each of these derivatives has error multiplied as a multiplier. In first 3 expressions, I have second derivative of input x, first derivative of input x, second derivative of output y of the adjustable system, first derivative of the output of the adjustable system, and the output of the adjustable system. So you see, it looks like these are derivatives of the particular parameters. Later, I will convert these derivatives into parameter values, and don't be surprised, parameter values are defined as products of the particular signals within the system. You never saw it in classical control, of course. Since derivatives of each parameter is defined, now I can define the these are derivatives rewritten, and I included constant C2, C1, C0, G2, G1, G0. They are constant parameters. I don't have to have different constant parameters. They could be all the same. But this is the definition of the optimal value of the parameter beta. It is equal to its initial condition plus constant times derivative of the times integral of the rate of change of this parameter. And this is true for all other parameters, and here it is implemented by simulations. Look, for initial conditions I chose all values of 1, which is not very fair, but nevertheless I chose them equal to 1, so I do not expect that initial discrepancy between reference model and adjustable system will be small. Parameter constant gain I chose to be equal to 500. And look what happens here. I have derivative integrated multiplied by constant gain with minus plus initial conditions, and this is the adjustable parameter B2, B theta 2, and so on, and so on. You obviously will get these materials available to you. These materials will be available to you, and of course you will be able to investigate it close. Finally, what you have is our system again. I have a special block that includes partial derivatives, special block of parameter adjustment. Let me see what's next. And the best what I can do at this point is to demonstrate the system to you in action. So this is the system that we've been talking about, but now on your screen you see the simulator. This is the reference model. This is the adjustable system as I explain it to you. This is the computational block that computes partial derivatives of the criterion with respect to individual parameters of the adjustable system. This is parameter adjusting mechanism, the adaptation mechanism. This is the constant gain. Actually, constant gain here I tried what, 7,000. I guess it's all right as far as it works. And I have the derivative integrated multiplied by a constant, and then I have minus and plus initial conditions. This is how I'm getting parameter B2 of the adjustable system. The best what I can do now is to show you the simulation results. I will say system and go. So here you can see the value of the criterion, and the value of the criterion approaches 0, which implies that the discrepancy between the parameter of the adjustable system and the output of the adjustable system and the output of the reference model is different, but the discrepancy decreases with time. So, and this is self-explanatory. Since criterion approaches 0, then the difference between outputs approaches 0 as well. But now you can see the value of parameter B2 of the adjustable system. It does not converge to the value of the true value of this parameter or to the parameter B2 of the reference model. It does not converge. And parameter A2 of the adjustable system also does not converge to the parameter value. Why it happens? It happens because we did not satisfy this requirement for local parametric optimization. We did not define the initial conditions of the adjustable system very close or sufficiently close to the parameters of the reference model. This is one reason. But then there is another reason. You know, parameter estimation works properly if and only if the input signal provides what is called the appropriate excitation of the system. And the requirements for this are quite rigorous. It is called persistent excitation. Input signal could become persistent excitation under several conditions, and some of these conditions are quite sound very outlandish. Now, are we still interested in being able to evaluate parameters of the unknown system? Yes, we are. But I will offer you in the second half of this course recursive least square method procedure that works much, much better. So parameter estimation could be left alone. However, the computation of the output could be very successful. You know what I will do? I will add simulation time to the system. I will run simulation for longer time, system properties, and I will run it for 9 seconds. Simulate and go. I want to make a point. Criterion approach 0 virtually. Time is still going on. But I want you to see the end of this process. Criterion began increasing. And let me run simulation for a little bit longer time, and I have a good reason for doing so. System properties, I will run it for 10 seconds. System and go. Don't be surprised when you will see the result of it. You see, parameters still do not converge to the appropriate values. The criterion reached the value of 0, but then I want you to see that the system becomes unstable and fluctuates. Why? Because you never heard about stability conditions being implemented in the local parametric optimization. This is the flaw of local parametric optimization in this particular application. What I will do now is I will consider with you an example of a very successful application of the MIT rule. Okay, local parametric optimization will be utilized. Now, look what I have. I have a reference model. And this reference model is a desired closed-loop system transfer function. I am dealing here with a very simple first-order system. This is the differential equation for this system. Okay, actually it's a first-order system, but I wrote its equation as I would be writing the state variable form, state equation. Look, derivative of the output or state is equal to fundamental matrix, it's minus AM times X plus matrix B times input reference signal R. Very simple differential equation. Why do I have minus here? Because it's a first order system. If I wouldn't have minus here, then the pole of the appropriate transfer function would not be in the left-hand side of the complex plane, and the system would be unstable. Reference model represents the desired closed-loop performance. It better be stable. For the controlled plant, I sorry. For the controlled plant, I have a differential equation written in the same format of a state variable, of the state equation, except it's a first-order system. And this is expression for the controller. It's a control law. Control effort is equal to some filter times the reference minus gain in the feedback times the output of the system. Very straightforward configuration of the system, except it's a simple system, much simpler that we would consider in our control classes. This is the error defined. This is the criterion. This is the criterion defined. It's error squared. This is the gradient rule applied. Look, criterion depends on two adjustable parameters: the gain in the reference channel and the gain in the feedback channel. Gradient rule has constant for this parameter times derivative of the criterion with respect to this parameter, and it comes with minus. It has constant for this parameter times derivative of the criterion with respect to this parameter, and it's also with minus. Can you look at the time derivatives? Let's look at the time derivatives. I honestly taking time derivatives of parameter W, which is gain in the reference channel, and I have this expression, and I have derivative of the it's derivative of the same parameter actually. So I rewrite this equation, and instead of having the sensitivity function here, I am using derivative of this parameter, derivative of the output. Actually, this is a sensitivity function. Yeah, I rewrote this expression using a sensitivity function. Similarly, I define derivative of the parameter W, finally, in this form. And I guess derivative of parameter F, gain in the feedback, would be defined in a by a very similar expression. Very similar expression. Now, what I would like to do is get rid of the sensitivity functions and the sensitivity function. So this is expression for the derivative of the output, and if I would rewrite this expression, we'll get this is the expression for the output. And let me tell you this, that the derivative, the partial derivative of the output with respect to parameter W is this. And the partial derivative of the output with respect to parameter F is this expression. Now, assuming that we are close, the reference model is close to the adjustable system, I will change these expressions as follows. Now, derivative of the gain in the reference channel is equal to constant gain times error, and this is reference input, and in the denominator I have the denominator of the reference model. As a matter of fact, this is the transfer function of the reference model. And similarly, derivative of the gain in the feedback channel is defined as the constant gain, of course with minus, times error, times the transfer function of the reference model, times the output of the adjustable system. And these are simulation configurations that give us a result in these expressions. What I would like to do now is to show you a simulation of a system like this in detail, but I will do it in my next lecture. So for today, I think we have enough information.